Hi everyone, welcome to this presentation on one of the key memory management techniques in operating system, that is compaction. This method plays a crucial role in optimizing memory usage and reducing fragmentation. In this video, we will understand what compaction is, why it's important, how it's work and when it's used. Let's begin. So, to understand compaction, we first need to talk about fragmentation. When memory is allocated and deallocated in a system over time, gaps or holes are created between allocated blocks. This phenomenon is known as external fragmentation. Imagine memory as a long shelf and books as programs. Over time, some books are removed and smaller books are added in between. Now, if you want to place a big book, even if the total space is enough, there is no single container slot. That's fragmentation. There is also internal fragmentation where a process is allocated over memory than it actually needs, but compaction is primarily used to resolve external fragmentation. So, what is compaction? Compaction is the process of moving allocated memory blocks together so that all free space is consolidated into one large block. It's like recognizing your memory shelf so all the blocks are grouped together and all the empty space is at one end, making it easier to add new books or processes. The operating system shifts processes in memory, updates references, and removes the scattered empty blocks. Why compaction is important? So, why is compaction essential? When a system runs over long time, especially one with frequent process creation and termination, memory becomes highly fragmented. Memory This leads to inefficient memory usage. Even if you have enough memory in total, fragmentation might prevent you from leading a large program. By performing compaction, the OS makes better use of memory and reduces the chances of allocation failure due to non-contagious free space. So there are three techniques for doing compaction. The first and the simplest technique is shifting all occupied blocks of memory towards one end, usually the start of the memory. Let's say block A, B and C are scattered with gaps in between. The OS will move them into the beginning of the memory, eliminating the gaps. This method requires the system to pause or delay process execution while the shift occurs. It also requires careful memory reference updates. This technique is suitable during system idle times and ensures that memory can be allocated in larger chunks again. The technique 2 is relocation with pointer updates. A more advanced method involves reallocating memory blocks and updating all their associated pointers and references. This means every time a block is moved, the system must go through and adjust every variable, data structure, or addresses that points to the block. This is particularly common in systems that supports dynamic memory allocation at runtime like those with garbage collectors. While these techniques offer flexibility, it comes at a cost. It's complex and requires cooperation between hardware, OS, and sometimes even the application. The technique 3 is a dynamic reallocation. The third method is the dynamic reallocation using hardware support like base and limit registers. Instead of changing the actual physical memory location, the OS changes the value in the base registers. So the program local address still works. This is efficient and avoids having to update every pointer or variable in the system. However, it requires hardware support and is not always available in simpler or older systems. When is compaction triggered? Now, let's talk about when is compaction used. Operating systems don't usually perform compaction all the time because it's costly in terms of CPU cycles and system performance. It is typically triggered in scenarios like first, when a large memory request fails due to fragmentation, Second, during ideal times when the system load is low. And third, the periodically as a part of memory maintenance in multitasking environments. It's all about balancing memory efficiency with overall system performance. Compaction becomes more important as the system load increases, with many processes running, getting terminated and new ones created. Fragmentation happens quickly. Without compaction, memory utilization drops and the system may need to use slower secondary storage for swap, affecting performance. Thus, in high demand environments, compaction plays a crucial role in keeping the system responsive. What are the real world use and efficiency of compaction? So some modern operating systems avoid traditional compaction entirely by using virtual memory and paging. However, embedded systems, real-time systems or any OS with strict memory limitations still rely on compaction. Even in systems like Java virtual machines, compaction is used during garbage collection to manage heap memory. What are the benefits of memory compaction? So, compaction enhances memory utilization by reducing fragmentation, allowing for smooth allocation and deallocation of memory. This leads to improved performance as it enables larger blocks of memory to be available for applications, ultimately enhances system efficiency. What are the limitations of memory compaction? So, compaction can introduce significant performance overhead, affecting system responsiveness. Additionally, it may require complex algorithms and processing time, leading to potential downtime. The process can also create fragmentation itself, underscoring the need for careful implementation. Let's recap the key points. So, fragmentation, first we have learned the fragmentation. What was fragmentation? The fragmentation leads to inefficient memory use. Com- Compaction solves external fragmentation by combining free memory. So there are several techniques for doing compaction, each with different trade-offs. So first we have learned what was fragmentation and how compaction overcomes fragmentation, and what were the techniques which were used by compaction for overcoming external fragmentation. And it's not done continuously but triggered based on need and system state. And why compaction matters. So understanding compaction helps you appreciate how operating systems keep your computer running efficiently even as applications are constantly loaded and removed. It's a key concept if you are studying operating system or working with memory constrained systems. So thank you all for joining me on this journey into the world of compaction and operating systems. I hope this clarified what it is, how it works and why it's essential. If you found this useful, be sure to check out more videos on OS concepts. Until next time, happy learning.